Today I'm going to quickly review quiz 1 that was due last Friday. And we have another quiz due this Friday. And then I'm going to try to finish up the lecture on SystemVerilog. And then I'm going to do a little, I'm going to talk about lab 2, and then I'll do a little demo for you. Okay, so quiz 1 was last week. I think there was 11 questions about SystemVerilog. I was just going to, also RISC-V assembly. So the first question was, consider the following C code and its translation to RISC-V assembly. What instruction is missing? So it's a for loop that initializes I to 2. Now in this case, I is actually initialized not to 2, but we're initializing it to 8. And the reason for that is because we're going to use I to walk through the array, because we're indexing this A array with I. So we're gonna be incrementing I in multiples of 4, and so we'll start it out as 8, and then we'll also use that to control the loop as well. Okay, so you can see that we load the address of A into x1, and we load 40 into x10. So 40 is meant to represent the loop limit here, which is 10, right? 10 times 4. And then we start out with the loop. And what's the first thing you do when you start a new iteration of a for loop? You check to see if you should continue looping, right? So you're checking to see if I is less than 10. So we should be using a comparison instruction. And in this case, probably the condition we want to check is the condition for exiting the loop, which is the complement of the condition for staying in the loop. So instead of checking to see if I is less than 10, we want to check to see if I is greater than or equal to 10, and instead of 10, it'll actually be 40, and 40 is stored in x10, right? So we're comparing x2, so we're doing branch greater than or equal to x2, x10, and then exit, right? All right, I forgot I had the little annotations on here. Okay, so there it is. Branch greater than or equal to x2, x10, exit, right? So basically we're checking to see if we need to exit the loop using I, which is x2, and the limit, which is x10, the iteration limit. Any question? Of course, both multiplied by 4. And then if you look further, we have instructions here for accessing A, for instance. So in this case, these two instructions, these two adds, are used to set up the address pointer for A. So we start out with taking x2, which is the index. We decrement 4 because we want to subtract 1 from this guy, right? So we subtract 4 because it's 1 times 4. And then we add x1, which is the base array, base address of A, and we add x3, which is that index value. And again, this is annoying, but this is the only way to do indexing in RISC-V. You have to basically use some add instructions to set up the effective address after you applied the index. You can't just do this with an index register inside the load instruction. And so, and then we just load the address of x4, which is this effective address, into x5. Make sense? Now, we could have probably just used -4 as the offset here, right? That would have worked too. That would have been a little better. That would have eliminated one of those instructions. Okay, any questions about that? So hopefully you guys are pretty comfortable with that, because you should have covered something similar to that in 212, if you still remember. Okay, this one says, what does the following code perform? So we have a shift left logical immediate, a shift right logical immediate, and then an OR. So we're taking the value in x3. So x3 is our input. We're shifting it left 16 bits. We're taking the same value in x3 and shifting it right 16 bits. And then we're taking the results of both of those and merging them together. So basically, we're going to put the upper half of x3 in the lower half, and the lower half in the upper half, and merge them together. So what that's going to do is it's going to take the two halves of the contents of register 3 and just swap, right? Swap them. So yeah, so x3 15 down to 0 is in 31 down to 16, and x3 31 down to 16 is in 15 down to 0, and then you combine them together. So again, just swap the two halves. What are two operations that you can perform on SystemVerilog code? That was just a multiple choice: simulation and synthesis. What's the problem with this SystemVerilog module below? You guys know? Anyone? Yeah, Z is in conflict. So Z is, you don't want to have two statements that both set Z, in this case two assigned statements. And there's actually another issue with this too. There's another problem. The other problem is that this assign is actually using Z as an input and an output. And so you end up with like a feedback connection. It's a cross-coupled connection. So that could lead to, having a statement like that could cause ModelSim to freeze up, because you end up with this combinatorial loop, right? The simulator keeps trying to update Z, but every time it updates Z, it has to update it again, because Z appears on the right and the left-hand side of that assignment, right? So the left-hand side of the assignment is updating Z, and the right-hand side of the assignment is acting as a trigger. It's causing that statement to trigger. So every time Z is updated, it re-triggers and changes Z potentially. So it's not smart enough to catch that? No, actually it's not, believe it or not. It used to be, I don't know what the option was. I think there might be an option, but it used to be when we used VHDL, if this happened, you would get an error message that said iteration limit reached. So there was a fixed iteration limit. It would limit the number of triggers per time step. So you advance the simulator, and if there was more than, say, 10,000 triggers, it would just bail out. But when we switched this class to Verilog, for whatever reason, it quit doing that, and it just went into infinite loop. There's probably a hidden option in there somewhere that you can use to set the iteration limit. But for whatever reason, by default for Verilog, there's no iteration limit. But even if you get the iteration limit, it doesn't tell you where the loop is in your code. Okay. Does SystemVerilog support structural or behavioral HDL? It's both. How many possible logic values can be assigned to type logic? This one's a little weird. I talked about 4 in class, but I mentioned that there's actually in SystemVerilog, there's actually some other ones that we don't use, but there's only 4 you need to worry about. That's Z, X, 1, and 0. Consider the SystemVerilog modules. What's the value of A and Y within my thing? So we have something called top. Top instances something called my thing. Top has both behavioral code in it with these with this assign, and structural code in it with this instantiation of this bottom module. And so inside top, we're going to put Y inside of we're going to connect the Y, which is hard-coded to 1, is going to be sent into the A input. So A is 1 in there. And then Y is assigned to be the complement of A, so Y should be 0, right? And complement 1. So 0, right? So Y should be 0, right? I get that right? Yeah, Y should be 0. Inside of my thing. But Y is actually 1 inside of top, right? So there's 2 different Ys, right? There's a Y inside of top, and there's a Y inside of this my thing, which is a bottom module, right? But those Ys are not the same signal. However, the Y signal in top is the same as the A signal in bottom, right? So those are shorted. Those are the same signal, but they have different names. Make sense? Okay. Assume the SystemVerilog code snippet. What is the value of A? Okay, now in this case, it looks like we're double driving A, but we actually aren't because one of those is assigning A to high impedance, so that's actually okay. So A would be 0 in that case. And how many bits comprise the signal A? 4. And to what value is A set in the SystemVerilog snippet below? Okay, this one is a little complex, right? So A is starts out as the value 2 encoded in 2 bits, so 1, 0, right? In binary, it's 1, 0, right? And then we shift it 1 bit to the left, so it's going to be 1, 0, 0, which is 4 in decimal, or 1, 0, 0. And then we check to see if that is equal to 4, which it is, right? Using the ternary. And since this is true, then the whole expression is going to evaluate to the true clause on the ternary, which is 1. Right? And so I listed the order of operations there, the precedence. So the shift happens first, the ternary happens second. The shift happens first, the equal is second, and the ternary is third. So that's the order of precedence. Of course, you can use parentheses in there if you want to make that more clear. So 1, right? Any questions about that? Okay. And last question, in the SystemVerilog code below, to what value is signal A set? So we've got, in this case, we've got A is set to 1 here. And then, well, actually, so my thing is driving A. Because, see, we've got A connected to my thing, but it's connected to this Y port, which is an output. You guys see that? So my thing is going to be driving A because A is connected to one of its only output, right? Which is the Y port. The problem is that we're also setting A here too. So A is double driven, but in this case it's double driven because we're setting it with behavioral code and with structural code. So we're setting it with an assign statement and we're setting it with this by virtue of having it connected to an output port of my thing, right? So it's set to 1 here, but what's my thing trying to set it to? Well, my thing is just an inverter, so Y is 0. So if we take Y in to the input on my thing, the output's going to be 0. So this line of code setting it to 1, this line of code setting it to 0, so it'll end up being X in the simulator. It's a conflict. Okay, so this is a good question, in my opinion, because this is a common thing that comes up in the projects in this class, is you may have something like this where it may not be entirely clear that there's a double-driven signal, because one of the issues with SystemVerilog is that it's kind of cool how you can see the port names here when I instance it, right? I can see that Y is connected to the A port and A is connected to the Y port, but there is no indication of which of these is an input and which is an output. That's the problem. You have no idea. By looking at this code, it's not clear what's an input or output, unless, of course, you name the things, like if you give these guys names that are a little bit more informative, right? Okay, so yeah, so you might say, well, how do you know? Well, then you'd have to drill into my thing and cross-reference those guys to figure out that Y is an output, right? Okay, that's it. Yep, it's X. Any questions? All right, good. So don't forget to take quiz 2. It's similar to this one.
Does it open today?
Yeah, it's open now, and it's available till Friday. Okay, so let's back up to the...
It's still showing that like no questions have been added.
Oh, okay. Sorry, that's my fault then. I'll fix that. Yeah.
And also, like,
I have them in the question bank, but I didn't actually move them over to the quiz, so that's my bad. Thank you. I'll fix it.
On the website, is it supposed to show everything like twice?
No, someone showed me that last week, and I don't see it that way. I need to see. This is what I see. I'm not seeing everything twice. I think what happened there was We have two sections in this class, and Ryan merged both sections into one. So we have section 1 and 2, and then what you're seeing on Dropbox is section 0, which is like a virtual section. I think something happened there when he did that. That should not be happening. I need to contact Ryan. Someone showed me that last week, and I just forgot to write to him. But I'll do that. There's nothing I can do about it myself because I don't have any kind of special access rights. Yeah, and I'll fix the quiz too right after class. Okay. Okay, so last time we talked about Verilog, and we pretty much got up and through. I talked about behavioral and structural Verilog, and we looked at some examples there. We talked about how to represent numbers. We talked about bit manipulations. Bit manipulations is, concatenating bits and replicating bits and slicing bits out of a bus. A bus meaning a multi-bit signal. We talked about reduction operators, and then I think I did a demo with ModelSim, right, where I showed a demo of that. And so generally speaking, you want to simulate your designs, and then when you're satisfied they work in simulation, then you put them on the FPGA. And you hope that if they worked in simulation that they work on the FPGA. It's not always the case, but usually. And I'll do a demo today of running these on the FPGA. Then I talked about Quartus. I think I talked about Quartus. Okay, and then I got to the always statement. So this was the last topic for SystemVerilog. So an always statement is a way to make a complex assign statement. And by complex, I mean that an always statement allows you to assign more than one output. And always only allows you to assign one output. Now, that's not technically true because you can use the curly braces. You could use the curly braces, the concatenation operator, to assign more than one output signal with an assign. Right? You guys with me? So, like you can say assign, and then you could do this trick where you say assign A, comma B. So technically, yeah, you can assign, like in this case, you're assigning A and B. But that's not super readable, right? With an always statement, you can have two lines of code inside the always statement that assigns A and B separately, right? That's the difference. So like you would say always, and then begin, and then end. And then you can say A equals B equals, right? So you can do something like this, right? So in this case, the always statement, you think of it like an assign statement because it's now the driver for any signal that's assigned inside of an always is now the kind of owned by the always block, right? Now you can assign it more than one time in here, but you can't assign it anywhere outside the always block because the always block now is the driver for A and B because you've assigned them in there. Does that make sense? Okay, so you can do that. The other thing you can do with always is you can use constructs like an if statement, a for loop, and a case statement. And you can call functions. There's various types of functions you can call. So it looks kind of like a more traditional programming language. And most importantly, always statements allow you to have memory. So you can have you can actually have flip-flops. You can make a flip-flop. Did you guys ever talk about flip-flops in 211? Yep. So basically, a flip-flop is a way to capture a bit and hold it over time. Usually, it's synchronized to a clock. And then RAMs. RAM is a memory structure where it's got memory, but it also has an address. So you've got multiple addresses inside that RAM that are individually addressable. Flip-flops don't have an address. Flip-flops are memory elements without an address. RAMs are memory elements with an address. And you can implement both with an always statement. Now this is where things get a little weird though, because always statements have something called a sensitivity list that goes after the always, right? So if you have an always statement, you have to put a begin and end on there if there's multiple lines of code, right? If there's not multiple lines of code, you don't need the begin and end, right? It's kind of like an if statement in Java, right? But there's this sensitivity list because with an assign statement, the sensitivity list is implied by any signal. So if I say C ampersand D here, C and D are the sensitivity list. If C and D change, it's going to activate that assign, right? So anything on the right-hand side of an assign is the sensitivity list. But with an always, because always statements can imply memory, you don't necessarily want to put all your inputs in the sensitivity list, right? Now, if it's meant to be combinational logic, just like a complex always block, then you do, in which case you would put always at star. So always at star is going to have the always activated on any signal that's treated like an input in there, which means anything that's used in an expression, right? You guys with me? So that's always at star. But that's the old way of writing it. That's the old Verilog way. The new SystemVerilog way of doing this is not to say always at star, but always underscore combinational. That's the SystemVerilog way, but that's up to you. You can use either way, right? You can say always at star, or you could say always com. Or if you really want to get old school, you could say always, not underscore, sorry, always at, and then in parentheses you can say, you can explicitly lay out your inputs. Like if this is C and this is D, you could say C comma D, right? Make sense? The risk, though, of doing that is what happens then if you say D and F. Well, now you've got F, which is treated like an input, but is not in the sensitivity list. So now this is memory. You're going to have memory in here, because basically what's going to happen is whenever C or D change, that's going to act like a clock signal for reading F, and this turns into a latch. Not a flip-flop, but a latch. It's going to end up being level sensitive, right? Unless, of course, you say pause edge in front of C and pause edge in front of D, in which case now it's a flip-flop. It's edge active. It'll activate on the edges of C and D. Rising edge. Rising edge of C and D. Then now I've made a flip-flop, right? But if I take the pause edge out, this is a latch, because C and D will act as the clock gate signal for F. Because otherwise F can change and it won't activate this guy. So what does that mean? It means that F is something that's only being read when C or D are set to some value, right? You guys, does that make sense? So if you're making combinational logic, you want to make sure that you always use always at star or always underscore com if you want to use the newfangled SystemVerilog syntax, right? Always com. Always com is safer, because if you accidentally do always, well, actually always com doesn't have a sensitivity list, so there's no way to make a latch that way by forgetting an input signal. But there is still another way that you could make a latch, because I could do something like this. I could still put always com, which is supposed to make combinational logic. By the way, are you guys comfortable with that term, combinational logic? Combinational logic means anytime any of the inputs change, boom, the outputs update, right? Because the output is only a function of the inputs. Whereas sequential logic is when you have some kind of memory going on in there where the outputs are a function of the inputs, but also the historical old values, the old values, the inputs from the past, right, somehow affect the present, right? That's a sequential logic, right? Okay, so let's say I put always com, but then I do this. I say if A equals B, then C equals 1 apostrophe B 0. What happens if I do that? Well, now I've got a latch again, because I only assign C if A equals B, but if I activate this always, if A or B change, they're implied to be in the sensitivity list. They'll activate the always, but then if they're not equal, once I get in there, I don't actually assign C to anything, right? So what is C going to be equal? It's going to be equal to the old C, right? It's going to be the historical, the remembered version of C. And again, this will create a latch, right? So you don't want to use latches. You never want to have latches in an FPGA design. And the reason is not because FPGAs can't make latches, because they can. You can implement latches on an FPGA, but it makes the timing closure very difficult for the tools. Timing closure is basically, and I have a lecture on this at the end of the semester, but basically timing closure is about calculating the critical path logic delay in your whole design, and then ensuring that the clock period is long enough to accommodate that worst case critical path delay, right? The problem is that when you have an edge triggered system, the critical path delay is measured from edge to edge. So you have from the rising clock edge to the rising clock edge. So you get a whole clock period. Whereas with a latch, you don't get a whole period of the clock, right? You just get basically the time the clock is low, right? Basically half the period. So your timing analysis from the tools is kind of screwed up, and you'll end up with a much slower clock if you end up using latches, right? So you should avoid using latches. So if you have code like this is valid code. Well, actually, it's not valid. You'll get an error because you explicitly said always COM. So the compiler would say, hey, I think you screwed up because you said always COM, but you got a latch in there, right? However, if you did this, if you said always at star, well, then it won't generate an error message, but it'll still create a latch. And this is essentially an unwanted behavior. This is a bug. So how do you fix this? Easy. You just put a default value for C right above that if statement. And then C may get changed twice, may be set twice, but only the last one will take effect, will matter, right? So that's basically always statements for combinational logic. And then you can also make memory. That's when you intentionally create memory. So in that case, you can say always at pause edge clock, begin, and end. And this will only activate on the rising edge of the clock. There's also neg edge clock, which is equivalent. Or you could say pause edge clock, comma, neg edge clock, comma, pause edge clock, in which case it's a DDR type system, double data rate, activate on the rising and falling edge of the clock. You can do that too. Make sense? Okay, so, and if you put always underscore FF there, that's the newfangled SystemVerilog syntax, that tells the compiler, yeah, I'm trying to make a flip-flop. So if it's not a flip-flop, according to your understanding of this behavior, then give me an error message because I messed up, right? So that's always underscore FF, optional. It's optional. Okay, now, one thing that you'll notice here is when I assign something in an always FF, I use a less than equal sign. Less than equal sign to assign signals, as opposed to an equal sign. So what's the difference? Okay, so notice, so here's an example over here. So this is a mux. I have an assign version of it. I have an always version of it. And notice I use an equal sign here, right? Just equals. Equals here, equals there, right? Simple. But then I get to, I have a resettable D flip-flop here. So this thing says always FF pause edge clock. If on the rising edge of the clock reset happens to be asserted, then clear the flip-flop. Otherwise, sample the D and stick it on Q. So this is a synchronous reset because this reset only works on the rising edge of the clock. Okay, but notice that I use the less than equal here to assign. Why? Well, this is the most confusing part of SystemVerilog. So there's two kinds of assignment statements in an always block, always statement. There's a less than equal version and an equal version. The less than equal version is called the non-blocking, and the equal version is the blocking. The difference is wildly convoluted. The only thing you guys have to remember is if you're making sequential logic with memory, use the less than equal. So if it's clocked, if you got a clock, if there's a clock signal involved, use less than equal. if there's no clock involved, then you're trying to make just a fancy assign statement, essentially, a more complex assign. By which I mean, like for example, this assign statement is just making combinational logic. However, it uses a case statement. So I'm trying to make some, I'm trying to make this look, it's complicated combinational logic. I want to use the case statement. I can't use the case statement unless I'm in an always. I can't use that in an assign. Assign is just a ternary. That's the best I can do, right? So if you want to use a case statement, you got to use an assign, which is fine. I'm sorry, an always block rather, which is fine, except notice I use the single equals because it's combinational logic, right? No memory, no clock. It's not clocked. Okay? All right, so that's all you have to remember. But I'll give you the real explanation. The real explanation is that with a non-blocking assignment, when you have a signal that's treated as an input inside a non-blocking statement, the value the always block sees for that input is whatever was previously assigned to that input. Okay, now this can apply to other things assigning that input inside the same always or in a different always. You guys with me? Which means that if I, for example, if I say D, N1 gets D, and Q gets N1, N1 on that second line of code, the N1 that it sees is not the version that was set in the line above it. It was set whatever was in the last time it was set on the clock edge. So what ends up happening is that this ends up creating a 2-cycle delay because it's going to take, I have to activate this guy once to get D into N1. And I have to activate it a second time on the next clock to get N1 into Q, right? So it creates 2 flip-flops in series, essentially. It creates a shift register, right? And the reason for that is because this second line of code, even though it appears after the first line of code that sets N1, it doesn't see the updated version of N1. It sees the old version of N1, right? Make sense? Why? Yes?
So like every time you're running it, then Q is just going to see whatever N1 was previously.
Right. On the previous edge, yeah, on the previous time it activated, right? Not on the current activation, on the previous activation. Yeah, yes.
So then every time that happens, when Q gets updated to the previous N1, N1 now is updated to the new D?
Yes, okay. Exactly, yeah. So N1 will lag D by 1 cycle. So N1 will be whatever D was in the last cycle, and Q will be whatever D was 2 cycles ago, or whatever N1 was 1 cycle ago, right? So it's a very common thing to do in signal processing if you ever take like digital signal processing where you have samples coming in and they sort of get shifted and you can see the last several samples, right, in order, right? That's what you're creating there, right? However, if you use the blocking assignment statement, then the second line of code will see the updated version of N1. But the problem here is that this basically will take this N1 and substitute it into the second line of code, right? So basically, this is equivalent to just saying D goes into Q, or Q gets D. So this actually creates 1 flip-flop, whereas this creates 2 flip-flops, right? This code is totally redundant. But it can still be useful if you have like a really complex expression that you want to kind of break into sub-expressions, then you would use this, blocking format. But on the other hand, if you just want to create a bunch of registers, use the non-blocking, right? But in general, like I said, the convention is that you should always use this for clocked and that for unclocked, right? If you forget, it's usually not catastrophic. But I've had some bugs that were really hard to track down because I accidentally used blocking in clock logic. And it wasn't even, and this is the thing that's crazy, the bug wasn't because of this happening where I had N1 assigned in here and then used in the same always. It turns out that this will bite you even if you assign N1 in another always, possibly in another file even, right? Right? Because it gets really complicated because you may have, if I have 2 always activated on the same edge, even if they're in different always in different files, they could interfere with each other through this blocking mechanism. So it gets really complicated and you can end up with a bug that's hard to track down. So that you should try to stick to the convention, okay? Okay, so that just describes that. Okay, last topic I want to cover are test benches. So I mentioned to you when you simulate your code in Model Sim, you can force your inputs to be certain values, right? You can just type force A, to be something and then run. Force run, force run, force run. So if you type force followed by run, force will set an input, so you can set an input for the design you're testing, and then run will advance the simulator so you can see what the effect of that input is, right? And then you just check and make sure things match up to what you expect. That's a horrible way of testing, obviously. It's not really practical to do that. So the way you're supposed to do it, especially for more complex designs, is to create a test bench. Test bench is just a SystemVerilog wrapper that goes around something you're going to test. And the wrapper does two things. One, it sets the inputs, and so you don't have to type, you don't have to write tickle commands in Model Sim. You can just have the wrapper set the input stimulus for you, the test inputs. And also, it can be self-checking. The test bench could check automatically the output from your design you're testing, and it can print an error message if there's a problem, right? As opposed to you trying to look at the waveforms, which is tedious, right? So, of course, you don't have to have the test bench do that. You can just have the test bench drive the inputs. It doesn't have to check the outputs, right? The other thing is, when it comes to the inputs and the outputs, you can either put them directly in the test bench code as constants that you type into the design, or you can put them in a separate file called a test vectors file, which is just a way for the test bench to read the inputs and the expected outputs from a file. That way, you can separate the task of writing the test bench and writing the tests. You guys with me? So that's called the test vectors, right? So here's an example. So I have this module called silly function. It has 3 inputs, 1 output. It just does some Boolean logic. And I can create a test bench. Now, one of the things you'll notice, by the way, is that generally speaking, all your modules are going to have inputs and outputs. They better. Because if not, they can't communicate with the outside world, right? However, a test bench is the exception. A test bench, because it's wrapping around the design you're testing and it's generating its own inputs, the test bench won't have any inputs or outputs. But keep this in mind, though. The test bench is not synthesizable. So only this is synthesizable, meaning anything you design that you want to put in hardware is going to have inputs and outputs. The test bench doesn't have inputs and outputs, but it's not something that's going to go into hardware. It's only for simulation purposes, right? So here's a test bench. Notice that there's no inputs or outputs there. It just says module test bench. It's kind of self-contained. And then you simulate this as the top level design in the simulator. And this thing will basically use an initial statement. The initial statement is used for initial conditions. And it looks kind of like an always, except there's no sensitivity list. You just say initial, begin, and end, right? And then you can put in A equals blah, 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 whatever your inputs are. And then, so that's kind of like writing force in Model Sim. But then how do you advance the simulation? You use this weird delay operator, #10. It'll delay for 10 time units, whatever the time units happen to be set up to be, which, as I mentioned earlier, it doesn't really matter what they are, because we're not simulating any kind of resistive capacitive delay here. So time is not really important here with the behavioral simulation, okay? So basically, you set A, B, and C, and then I just give it enough time to do its thing. So #10 semicolon. By the way, this is what automatically disqualifies this from being synthesized, by the way. You cannot synthesize any module if it has this hashtag thing in it, because you can't do that. You can't design hardware and have it delay for 10 time units. At least not without like having an like a clock and then counting cycles on a clock and some kind of external time reference of some kind, right? So doing this delay thing makes this non-synthesizable, but it'll work in the simulator, and when you're happy with it, then you take the thing that you're actually testing and you're going to put that in the hardware. And then presumably you're wiring A, B, and C to some wires coming from the outside world or from the module, right? Okay, you guys with me? Okay, so this thing, all this one does is drive the inputs and delay. So the expectation here is I'm going to load this in the simulator and run it. I'm just going to look at the waves, right? But that's not real practical. So instead, I can add some if statements in here to check to see if the output matches what it should be, right? So now I've got this notion of the actual output, Y, and I've got an expected output, which I've just hard-coded, right? So that way I basically set my inputs, delay, and then I check the value to see if it's expected from whatever the previous inputs I put in there were, right? And that way I can print little error messages. Now I've got this little function I'm calling called $display. Now $display, I think you can synthesize code with that in it, but that would just get ignored in the synthesized code, because $display is designed to print a message to the simulator console. There's no simulator console if you put this in hardware, obviously. This is only for simulation, okay? So you could print a little error message. So the idea here is that you essentially just load this in the simulator and run it, and if it doesn't print anything, then it's working. If it prints an error, then you have to bring up the wave window and start drilling and trying to do some forensics, find the bug, right? But if it doesn't print anything, assuming of course you ran it long enough, how long do you have to run this for, by the way? 1, 2, 3, 4, 5, 6, 7, 8. It looks like 8 test cases, which makes sense. There's 3 bits input and 2 to the 3rd power is 8, right? So like 8 times 10. So you'd have to run this for 800 time units because it does a fully exhaustive, set of input values. Okay, now the problem with this, of course, is that you have to hardwire this stuff in here. You have to hardwire the inputs and the expected outputs, which that's not practical. So what's better is to write a test bench with test vectors. Now the problem with this is you have to figure out when you write a test bench how you're going to synchronize. When you set the inputs, even on a combinational logic circuit, now I mentioned to you guys, let me clarify something just to make sure I didn't confuse you with this. When you simulate behaviors with like combinational logic, it's infinitely fast, right? The circuit is infinitely fast. But it still requires a non-zero time. So the reason why we have these times in here, this hash 10, is to give it some amount of time, but it doesn't matter how much time, for the outputs to update after you change the inputs, right? So remember I mentioned that in ModelSim there's this notion of a sensitivity list where you activate things, you activate circuits to update their outputs. You have to give it some non-zero amount of time for that to happen, right? Doesn't matter how much, right? So that's why these little hash 10 things, pound 10 things are here. Another way to do it is you could use a clock signal. So for example, you could assign the inputs on the rising edge of the clock, and you can compare the outputs on the falling edge of the clock. That's just another way that you can coordinate the inputs and outputs, right? Or you could still put in little hard-coded delays. You could still do that, but this is just another way to do it. And so, so then you can write a test vector file, which is this text file with just bits. So these are the bits, these are the input bits, and that's the expected output bit. The underscore is ignored, but it's useful for me so I can see the difference between the inputs and the outputs. And then you can combine this with a load for that. So let me show you. So we've got this test bench, and I've got the silly function instantiated in there, and I call it DUT, which stands for design under test. And then I wire up A, B, C, and Y, which I've declared above. I also have a clock, a reset, and then I have a vector number and errors, which is just a counter, 32-bit counters. And then I have, this is new, this syntax, test vectors. This is an array of vectors, an array of multi-bit logic signals, right? But this syntax is really obnoxious because remember how I mentioned earlier that when you make an array, a multi-bit signal, you have to put the numbers before the name, which is unlike any other programming language array syntax, right? Usually if you have an array like in C or Python or Java, you put the size of the array after the name of the array. Well, here you have to put it before. But this is where it even gets stranger. If you make a two-dimensional array in Verilog, then you put the other dimension after the name. This is also the syntax for declaring a RAM array. Okay? But here's what's confusing about, you might say, what's the big deal? It's just where you put the indexes. No, the crazy thing is that in C and in Java and C++, Python, I should say NumPy specifically, and in linear algebra, the row goes first, the column goes second when you have a two-dimensional array, right? Row, column, meaning that the depth comes first, the width comes second, always, right? Make sense? That's how it works in program, usually, right? Which is kind of weird because like in a Cartesian coordinate system, it's actually switched. You've got x and y, where x is the width and y is the depth, right? But in linear algebra, it's swapped. You've got the vertical component, then the horizontal component, right? Okay, now in Verilog, they swap it. They have the width goes first, and the depth goes second. So what this means is the test vectors are 4-bit wide each. Each test vector is 4 bits. But I've got 10,001 of them in the depth, the array. So I've got 10,000 test vectors, each of which are 4 bits wide. But again, keep in mind, this is the opposite arrangement that you have in C. In C, it's row, column. So you could think of this as the column. There's 4 columns, 4 bits on the columns, but 10,000 rows, 10,000, that's the depth of this memory array, okay? So this is the opposite of what you're used to. Make sense? Okay, so what are we using that for? Well, basically, it's a lot of explanation for something that's actually pretty simple. You just use this function in the initial block. Initial just is at the beginning of the simulation. You say $readmemb. You give the file name and what you want to read, and this readmemb stands for read binary data. This will just take the data in your file and it will put it in that test vectors array. That's it, right? And then you initialize the counter, the vector num counter, and you tell it to reset. You give it a reset pulse. You set reset to 1, give it a little delay, and then set it to 0 permanently, right? And then end, right? And so then you can have an always that activates on the positive edge of the clock that takes the vectors and puts them on A, B, C, and Y expected. So this is the format I was telling you about where you can use the curly brace to actually assign multiple values in one line. A little confusing, but this is the syntax the book used. I probably would have done it in multiple lines, but that's one way to do it. And then on the negative edge of the clock is where you actually look at Y and Y expected. Right? Y expected comes from the test vectors, and Y comes from the DUT. As long as they match, we don't have any problem. If they don't match, then we've got an issue. So on the rising edge, we blast out the inputs. The falling edge, we check the outputs, right? And so for that, we have 2 always statements. The first always sets the inputs. The second always checks the outputs. The first one's on the rising edge of the clock. The second one's on the falling edge of the clock. Make sense? And then we have another always. Oh, actually, no, I'm sorry. This is all part of the same one. In the same always statement, we check Y if Y is Y expected. If not, we increment the error counter and then display a message. And then this part here checks to see if the vector that comes out of the vectors array is an X, which will happen after we read past the last vector stored in there. So this is just a stopping condition. And then finally, if that's the case, then we have a finish, which stops the simulation. Make sense? So this is the first time I think I've showed you multiple always now that are working together, at least in Testbench. I'll show you another example here when I demo the code from Lab 2. And that's it. That's all the SystemVerilog stuff. Any questions about that? Okay, so now, by the way, this is, I don't expect you to memorize the syntax. Even I often have to go back and refer, because the syntax is so bizarre. Anytime I do a lot of SystemVerilog programming, I always have to go back and check a reference. Yes?
Like on the midterm and stuff, if you ask us questions about code, are we allowed to use any references?
Yes. Oh yeah. Yeah. It's all open book. Yeah. Yeah. Yep. Yep. Open book, open internet. Okay. But there's a time limit though, right? Okay. So
This electronic book app here pretty fast though.
The midterms in person?
no, it's on
Just online.
online. All right. So next thing I want to do is talk about Lab 2. I don't know if you guys have had a chance to look at that yet. Lab 2 is already put on the website last week. Okay, so the objective here is we want you to just create a 7-segment decoder, which can be done. It basically can be done with a single assign statement with a nested ternary operator, or you could do it with a case statement or an if then else and an always. But you could basically do this lab with just one always or one assign. So it's pretty simple. It's meant to be a tutorial, but it also requires you to actually get the FPGA working. So there's some other details aside from the SystemVerilog in terms of getting the tools working and stuff. But the idea is that there are 8 7-segment displays on the board, and there are 18 switches. And so we just want you to wire each group of 4 switches. So 18 divided by 4, 4.5. Yeah, there's 16. There's 2 left over. So it's like you get basically 4.5 digits, hex digits worth of switches. And you just want to wire those to a decoder that will go to each hex digit on the board. So the hex digit is a 7-segment display that can display values from 0 to F in hex, right? So if you put all 4 switches up, it should be F. If they're all down, it should be 0. If you have 1, 0, 1, 0, which is 10, there should be an A on there, right? So you have to figure out how to form each one of those characters. Yes?
So since we're only using 4 on this, I'm just curious if you wanted to use the full 7, would you just have to make it like 3 bits per?
You could do that. Yeah, that would be one option. But we assume that when this gets done, the first 2 digits will be probably 0, I assume, or blank. 0, yeah. And the third one from the left will just go from 0 to 3, right? Because there's only 2 bits worth on that. And so each one of these decoders will be a module that you create, and then you can copy and paste it, or you can use a generate loop, which I haven't talked about that, but you can look it up. There's a way you can just write a for loop to generate 8 of these things. And 4 bits in, 7 bits out. So 4 bits come in, 7 bits come out, but the 7 bits are wired to each one of these little segments, and you have to look at the, there's a manual online that tells you how to look at the DE2 manual. The segments are active low, meaning that 0 turns them on, 1 turns them off, and they are ordered from least significant to most significant, in which the order starts at the top segment and goes around clockwise, and then ends with the middle segment. Unfortunately for us, 7-segment displays usually have a decimal point, and these ones have a decimal point, but it's not wired to the FPGA. So we can't use it, which sucks because we actually do need it in Lab 4. We need a decimal point, but it's not wired. Just like the LCD display on here has a backlight, but they didn't wire the backlight bit, so we can't turn on the backlight. So some of the things aren't wired up on here, but that's okay. Okay, so how does this all work? Well, you just download the project skeleton. I ran this one. Yeah. Okay, so you download the project skeleton, and it doesn't have as many files as I'm showing here. The reason I've got all these files is because these were generated when I built it. When you do a build, these are all intermediate files. The actual project skeleton has like maybe I don't know, 8 files or something, right? So I want to call out a few of these. So you've got a file called top.sv, and you got a file called simtop.sv. And there's also one called hexdriver.sv. Those are there to help you get started. There's some code that we provide. Simtop, you probably won't use Simtop because, actually you might, I have to go back and look at that. I forget if we asked you to do a test bench or not.
Yeah.
Okay, yeah, sorry. You will use Simtop, sorry. So Simtop is the test bench. Simtop is a test bench that wraps around what would be the top level design for the FPGA, right? So Simtop is acting like it's the board in your eyeballs when you're using it, right? And so you're going to write test vectors for that. Top is the top level design for the board for the FPGA, right? So when you put this on the FPGA, you're going to start with you're going to synthesize top. When you run it in Model Sim, you're going to synthesize sim top. Make sense? Right? That's the difference. Now hex driver is that's basically blank. That's just for you to put your 7-segment decoder code into. And you don't even have to call it hex driver, I don't think. You can call it whatever you want. We just gave that to you as a starting point, okay? Now, one thing you'll notice, though, is if you open SimTop, I don't think there's much in there. Yeah, it's pretty much empty. It's just SimTop, no inputs. Hold on, can I? Hold on one second. I want to see if I can change set title, view, preferences, appearance, colors, appearance, background. Isn't there a way? I thought there's a way you can set presets. Black on white. There we go. There we go. That's easier to see. Okay. Okay. So I'm going to make this a little bigger. Okay. So no inputs or outputs, right? But I have intermediate values for the hex, and then I have a DUT, a design under test. And this is just placeholder, right? Okay, so then if I open top.sv, this guy has some more stuff in it, and I just want to explain what's going on here. So this module, see, it says it was generated by Terra 6 System Builder. So there's actually a tool that comes from the company that makes these boards that generate these, like the top level design for you. And the inputs and outputs have special names that correspond to the pin mappings that actually map to the pins, right? And you can see those pin mappings if you look at the project file, right? So basically all the top level signals have to have names that match up to the actual pin names for the FPGA. Now you'll notice I guess it generated this. I thought Charles might have wrote this because he's got all the crazy tabs on here that line, the formatting is set up to kind of line things up in columns. So there's a clock 50, clock 250, clock 350. I have no idea why there's 3 of them, but we just use clock 50 later on. For the hex display, it doesn't matter because we're just making combinational logic, right? But clock 50 is the 50 megahertz clock that comes in from the board. I assume clock 2 and 3 are also 50 megahertz. They have 50 in them, but we've never used them. Okay, then you've got LED G and LED R. So there's 18 red LEDs and 8 green LEDs. And then there's 3 keys. Keys are the buttons. They're active low, by the way. So when you push them, they're 0. You release them, they're 1. And then 18 switches are these switches. And then you have the 7-segment displays that come out, right? They're just named hex 0 through hex 7. So there's 56 total wires that come out that connect to those hex displays. And then we have some stuff in here. So this is kind of an example design that we've got. So, and this is in here so you can make sure your hardware is working. It's like a sanity check, right? It's kind of like a demo code. So we have this thing called clock div. And it's a 24-bit signal. And the way this works is that there is an always in here that increments. Oh, this is okay. Hold on a second. Sorry. Thought I had updated. This is my changed version. I want to get the original version. Let me grab the original version here. Let me remove lab hex. And then lab hex dot. Yeah, here we go. Sorry. Lab hex. Top.sv. Sorry, I had a modified version. Okay, this is the original version. So there's several always in here, but the first one you see is this one that just adds 1 to clock div. Okay, so clock div is a 24-bit signal, right? And we're adding 1 to it every clock cycle, which runs at 50 million times per second, 50 million cycles per second, right? So what that means is that the 24-bit counter will roll over to 0 after 2 to the 24 bits, 2 to the 24 clock cycles, right? Right, which is it's about 16 million, right? 2 to the 24th power, right? So that's going to roll over at a rate of 50 million divided by 16 million hertz, right? And then we take the most significant bit of that counter and we use that to, where's it at? Where's it at? Where's it at? Where's it at? Right here. We take the most significant bit of that counter, bit 23, and we assign that to LED clock. So what that does is it creates a divided form of the clock. It takes the 50 megahertz clock and it divides it down into a 2 hertz, 3 hertz, 3 hertz clock, right? Why would we do that? Well, because we want the board to do something that we can see. Because anything the board does at 50 million times per second is not going to be visible, right? So basically we have this slowed down version. And then we have some code. Oh, by the way, also, this code is going to take, we have a thing called LEDs, which is 26 bits. And we use that to assign the upper 18 bits to LED-R and the lower 8 bits to LED-G, because those two banks of LEDs are next to each other, right? So we have this one LEDs array, which maps to all the LEDs, even though some of them are red, some of them are green, right? And then we have this thing called LED state. So what that does is, well, okay, it says in the comments, but basically what that does is that we're going to take the LEDs and light them up in sequence. We're going to have one LED on at a time and just have it walk to the left and then walk to the right, right? So LED state controls which direction it's moving, right? Okay, and so and the code down here basically just does that, right? So this isn't always, it's activated on the LED clock, that's the slow clock, and so there's an if then else that controls, you know, when we change from left to right mode, and also it uses a shift operation to actually move the LED. Now, when Charles wrote this, he did not use the, you know, width designator for these things, which is not good, but it still works. Okay, and that's it. So if you want to use this, if you want to test it out, all you have to do is run our script, CSCE 611, compile, and this will synthesize the code using the tickle interface, the command line interface, of course. You can also do this in Quartus. All you have to do is open Quartus and open the project file and you're good to go. You hit go and you're ready. But this is just a little easier. You can just do it at the command line. You can see there's a bunch of messages kind of flying by, and sometimes it makes it easy to miss legitimate warnings. Okay, so it finished. That's not too bad. That's actually pretty fast. So CSCE 611, I can do now program. And let me check. It says it's not detected. LSUSB. Oh yeah, because I'm not plugged in. Sorry. Hold on, plug in. Oh, by the way, these boards have 3 USB connectors on them. You want to use the one labeled USB blaster. That's the leftmost one. That's the programming cable and the debug cable, basically. The other ones are if you actually want to implement a USB device on the FPGA. Like you can build your own USB device. One of these would be a master, one of them is a slave. Okay, so got the cable and plug it in. And once that happens, I type US, I could type LSUSB, I can see it's connected there. And so now I should be able to program. And so when it starts programming, you'll notice that the board goes kind of dim. These guys go into tri-state, which is why they go dim. And then you can see the LED now walking across You see that? You guys can see that? It's going now. Kind of just going back and forth. Right? So this way, if you suspect there's a problem with your FPGA board or your cable or whatever, you can just run this demo, and this is a sanity check. It's like a self-check, self-test sort of. Okay, so what if we wanted to change this now? So let's try to do something interesting with this. So if I open up top.sv, okay, so what if I wanted to do something, like this is not interactive at all. Like, so what if I wanted to basically use the switches here, right? Which, you guys will have to do that for the lab. So let's say I wanted to do something where when I flip a switch, it doesn't matter if I flip it up or flip it down, the design will then light up the corresponding LED. And then if that switch corresponds to an LED on the left side of the board, it'll walk it to the right. And if it's on the right side of the board, it'll walk it to the left. Right? Now it's a little weird because I only have 18 switches and there's 26 LEDs here. So it's a little bit of a mismatch. But how would I do something like that? So I am going to, I'm actually going to wipe out this code that actually controls that walking back and forth. And I'm going to create another always here called, say, always at pause edge. I'm going to use the LED clock for this. Begin, end. Okay, and then I need to check to see, I want to detect edges of the switch. In other words, changes. How do I do that? Well, in order to do that, I need to create something called LED old. I need a value that will keep track of what the, not LED, sorry, switch old. Switch old. I want to keep track of the old value of the switches. You guys with me? So like if I flip a switch, I want to be able to compare the current value of the switches to what they used to be, right? So I'm just going to say switch old equals switch. Right? So that'll create a one cycle delayed version of switch, like in a register, a flip-flop, right? And then I can have something called switch diff, which is going to be switch XOR switch old. And I have a typo in there. It should be switch old. Switch old. Now, by the way, why am I using SW? SW just happens to be the name of the actual, that's the name of the actual switch input, 18 switches, right? So I've got switch old and switch diff. Make sense? Okay. And then I can say, now, by the way, notice I use blocking assignment. So it's going to take 2 cycles. It's going to take a cycle to go from switch to switch old and then another cycle delay, to calculate switch diff, which is fine because it's, I'm not going to notice that. Okay. Then I can say if switch diff doesn't equal 18 zeros, then begin and end, and I can set LEDs to be whatever switch is. Switch diff, whichever one changed. Okay, so when you do an XOR, that's basically going to put a 1 bit wherever there's a difference, right? And all the other bits will be 0. That's what an XOR does. It's a differencing operation. Whenever you have a 0 and a 1, you get a 1. If you have a 0, 0, or 1 and 1, you get 0, right? Okay, so then I can do that. Else, okay, now this is where things get a little weird with the begins and, okay, so, sorry, this needs to be begin and, so this takes a little get used to, right? So you've got, if this syntax looks like C, right? But then I have to put a begin, right? Then I got to put an end, but then the else comes after the end, right? And then another begin and end, right? So that kind of looks cumbersome compared to C or Java. Now I didn't actually need to put begin. I could have actually gone without this begin and this end, because it's only one statement there, right? But down here, I'm going to say, I'm going to replace Charles's code now that says, oh, by the way, sorry, take that back. I do want to begin and end here because I have to take care of the direction. So I want to do that, but I also want to set the direction. So LED state is going to be equal to what? I'm going to say if switch diff, and then I'm gonna shift this. How many do I have? 18? Yeah, but I'm gonna treat it like a 26-bit array actually. So I want to do like 13. So I'm gonna shift it. I'm gonna shift it 13 bits to the right. So that'll tell me if I'm in the left side of the switches, right? But I'm gonna treat. You know what? Yeah, it's a little weird because there's only 18 switches and there's 26. But I'm going to do 26. So I'm going to shift it by 13 bits. So I'm going to just shift it like this, 13 bits. So I'm going to do that, and I'm going to say if I shift it 13 bits to the right and it's 0, so how many bits is the switch? 18. So if that's 0, then that means that whatever switch I swapped, or whatever switch I flipped, was on the right-hand side, so I want to shift the thing to the left, right? So I need to set LED state to be left, which one is left? 0 is left. Yeah, I want to set that to 0, right? So 1 be 0, and then I'll say else LED state 1 be 1. Cool. All right, that's it. And then in the else block here, I'm just going to say if LED state if LED state, then I'm going to say LEDs is LEDs. 0 is, sorry, which one is 0 again? 0 is left, yeah, so I want to shift to the left. So shift 1 bit to the left. Else LEDs is assigned LEDs, shifted 1 bit to the right. Cool, and that's it. I think I got it, right? Now the only thing is I forgot to declare, I got to declare switch old and switch diff, which I will both declare as 18-bit signals, so 17:0. And anything else? No, I think that's good. So where's the but? I know there's probably an error in here somewhere. I'm sure of it. Always begin, end. That if is begin. End is there. If this doesn't have a begin and end. And, this one, else begin and, yeah, but this begin and end is there. That begin and end is there. There's no begin and end there. And the begin has a begin there. Oh. And, okay, I think we're good. Does that look good? All right, let's see if it works. I'm sure there'll be something I have to fix, but let's try it. Might just have enough time if I didn't screw this up. Well, looks good so far. Oh, wow. Okay. Now, by the way, this one, once the light shifts off, it's just gone. So it shifts and then it moves and it disappears because I didn't have the reversal. I don't reverse the direction once it hits the end. All right, come on. There we go. Almost there we go. I got it. Cool. All right, program it. And come on, baby. Okay, well, the light's moving. Okay, it's gone. Now, if I hit this one, oh, it worked. See, I hit the one to the left, or I hit the one to the right and it shifted left. What about this one? Oh, did that not work? Oh, yeah, there it goes. Yep. Sweet. Now, notice I hit the leftmost switch. The light didn't start on the left because, like I said, there's more LEDs than there are switches. So when I hit the leftmost switch, that's actually 18. So it's going to activate. It doesn't matter if I switch it up or down, but it's going to activate LED 18. LED 18 is still more than halfway across, so it's going to move it to the right. But if I do LED 0, then it moves it to the right. You see that? So yeah, cool. I didn't think that would work. Okay, any questions? Okay, so we'll be working on the lab in lab. Let us know if you have any questions. Don't forget about the quiz.